Let me get my remote. So, thank you for inviting me, organizers. And it's my absolute honor to be here, to be speaking with you. Thank you for everything that you had to do to be here. So, tonight I'm going to talk about building superstar clusters. So, this is my thesis work that I'm getting close to graduation, getting my PhD. And so, this talk will surround my dissertation, basically. But before that, let me give a plug for another project that I'm involved in. So this is called Astrobytes. So if you don't know it, you can type astrobytes.org or .com onto your web browser. You will be brought to this amazing page. So in short, what is that? So it is a very digestible astronomy research page that you can get the most recent astrophysics research explained in a very easily understandable form. So we have latest paper, and then sometimes we will talk about our experience as a graduate student, or we sometimes we also talk about career navigation, how to apply for graduate school. So it is good for everybody. And if you're an undergrad, you want to submit your research, we also have a link up there that you may not be able to see it right now. So, but there's a link there you can submit your research and then as a guest post. So, this idea has been brought to other subjects too. So, including astronomy in other language, Spanish and Farsi, and other subjects like evolutionary biology, chemistry, particle physics, environmental science, oceanography, and then soft matter. So, this is an rapidly expanding collaboration that we're building. So I'm very proud to be sharing this with you all. So that said, let's dive in. So this talk will be mainly about superstar clusters. And the main idea that I want to get across is they are extremely dense and they are extremely bright. So as you can see from this image, so I'm showing the gas density at the very core of a forming star cluster, in particular, a forming superstar cluster. So they have mass that are a million times the sun, and they are extremely compact. So in here, it is about 2 or 3 light years across, and we have a lot of stars. They are really dense, and if you pack stars really close together, their radiation or their starlight is very intense, and they will have the influence on the surrounding gas. What you're seeing here is the gas around a superstar cluster. Red means high density, blue means low density. So before we can actually talk about superstar clusters, let's start with the most familiar star that you know. So what is this? Yeah, so this is the amazing picture of our sun, and you can see the sun itself is very complicated. It has corona, it has a lot of internal structure, it has sunspots, but let's just put it at the corner. So we have the sun here. So what is the next closest star we have? Exactly, Proxima Centauri. So let's put it there. So what is the separation between the sun and Proxima Centauri? Wow, you guys are amazing. So it's about 4.2 light years, right? So it may sound really close, but that's actually like really far away. So to give you a conceptual understanding of how far away it is. So let's take the sun. I'm not strong enough to take the whole sun, so I may need your help. So if we take the whole sun and then shrink it to the size of a basketball. So and then put it, let's say, on a table here. And so since Proxima Centauri is a lower mass star, it's roughly 10% of the mass, so it will be smaller. So it will be a ping pong ball on that scale. So basketball for the sun, ping pong ball for Proxima Centauri. So on this scale, where do we find this Proxima Centauri? So let's say the sun is right here on the table here. So how far is that ping pong ball? Is it like far away at UT campus? Is it what? Oh yeah, so everybody knows the answer. So It will be in London. So just take a moment to comprehend that message. So if we have the sun right here, the next closest star is in London. So the takeaway message is space is actually full of space. So we have a lot of space in between. So in our neighborhood, so around our sun, so we have a lot of space. But to be a little more concise, the space is filled with what we call interstellar medium, or we call it ISM, if you want to impress your astronomer friends. And so interstellar medium is basically a mixture of gas, mostly hydrogen and helium, and some dust. And so on this scale, this is our neighborhood. So in superstar clusters, what we will have is, instead of just gas and dust, we will have about a million stars, and they are as bright as 1 billion times of the brightness of the sun. So when I was making the slide, I was trying to make a really cool visualization so that you can understand, oh, superstar clusters are actually really amazing. And then I realized actually nature already did the job. So this is one of the very prototypical superstar clusters, what we call R136. So it is in the Large Magellanic Cloud. It's a satellite galaxy around the Milky Way. So as you can see here, so this is the cluster, R136. It has 100,000 solar masses. So there are a lot of stars here. And look at the scale. There's only roughly 10 light years across. So if you look at this picture, it's really pretty. And the other message you want to get out of is, in order to form this thing, we need to compactify a lot of gas. A lot of gas, yes, really a lot of gas in a very small volume. So how do we get this? So one way to actually achieve this is through what we call galaxy collision or galaxy merging. So this is an example of the galaxy M81 and M82. So they have undergone a collision hundreds of millions of years ago, so really long time ago. And that actually left some evidence on this galaxy M82. So if we actually zoom into this galaxy, this is what you will see. So on the left-hand panel, we have the zoom-in image of M82 in optical light, so visible light. And in the middle panel is the same region, but in infrared, so in heat vision, basically. So in a visible image, you see stars, starlight, and see some dust lanes. So they are the cold dust. And I would want you to focus on the middle panel, because every single white dot here is a superstar cluster. So as you can imagine, hundreds of millions of years ago, two galaxies merged each other, go across each other, and then that compression of gas make a lot of superstar cluster right here. So every single white dot. So you can imagine every single white dot is inside is a superstar cluster. But don't get mixed up. So this is R136 in Large Magellanic Cloud. That is M82. So they are not actually in. This is not actually in that region. I just want to give you a concept, give you a mental picture of what is actually contained in each of this white dot. So this is observation. We see this. They are almost everywhere. They are amazing. They are really pretty. And as a theorist, it's just too much for me. As a theorist, I want something that I can easily understand. So in order to figure out how to build these clusters, I start with really simple picture like this. So to build a superstar cluster, what do we need? We have millions of solar masses, right? So we need millions solar masses of stuff, of material, of gas. So we have a cloud, very large gas cloud. So if you just let it sit there, what will happen? It may disperse, but in those compression that we just saw, like when two galaxies bang with each other, and the density will be so high, and actually they will not disperse. They will collapse on its own. So in the more dense location, it will condense into denser gas clumps. So at the end of the day, we will have a cluster of gas clumps, denser clumps. And then if we let it sit there for a even longer time, density will increase, and we will actually form stars in the gas clouds. And after the ignition of stars, because they are really dense, the starlight from the stars, are very intense. So they will heat up the gas, they will push away the gas, and at the end of the day, what we will have is a star cluster. So this is extremely easy on this cartoon picture. However, if you actually want to do a PhD and learn about this, perhaps you need to add like 10 question marks on each of the arrows, because in each of the process, you can write hundreds of dissertations and papers on it. So it's actually very, very complicated. So the bottom line is gravity wants to pull stuff together. So you have a gas cloud, gravity wants to pull everything together and form stars. On the other hand, starlight want to push things further away. They're going out. It's shining light, right? So it is effectively a tug of war between gravity and starlight. So, and in reality, we don't have cartoon pictures like this. So the actual physics is kind of complicated. So as a theorist, I would like to understand this, but I need some help. So what I use supercomputers. So on screen is the STEMP2 supercomputers here at UT at the Pico Research Campus. So it's an amazing supercomputer. So in my research work, I replace the complexity with sophisticated physical model, run it on supercomputers. And so we have the two now. So we have the STEMP supercomputers. In order to actually learn about how superstar clusters form, we need to get the large gas clouds, right? But it turns out supercomputers, they don't understand a cartoon cloud. So that's a little tricky. So we need to actually run simulations on in order to make the gas clouds that make the stars. So after some simulation, you get the more realistically looking gas clouds, and then we fit it in the supercomputer. And of course, the supercomputers, they don't know physics, right? You need to teach them physics. You need to put in the physics there. So these are equations that I actually use in my simulation. You don't need to understand this just to impress you. And so after we have this realistic gas cloud and the physics, we can actually start the simulation. And this is the actual visualization that I'm going to show you. So this is actually taken from my research paper. And if I can get it to play. So thanks. So one thing, so it's similar to the image that you saw before. Red means high density and blue means low density. So you can see it's a turbulent, very chaotic gas cloud. And as I hit play, you will see black dots forming on the screen. Those are the actual stars formed in the simulation. So let me get it to play. So you see, from the visualization you see gas cloud, they are forming fingers, and they are just merging with each other, and stars keep forming, and at the end of the day you have a really massive superstar cluster in the middle. And you may want to see a zoom-in view of that simulation. So this is the image that I show. So this is the center of that superstar cluster, and we see there's a chaotic distribution of gas around it. So the bottom line, the takeaway of this simulation is, you see the gas distribution is very clumpy. So clumpy gas actually weakens the force of starlight. Why? Because when stars shine, the starlight tends to stream through the low density channel. So they try to take the path of least resistance. They're not actually imparting that much force on the gas clouds around it. So the bottom line is this irregular distribution of gas flavor gravity in the tug of war. So this is the conclusion basically for my dissertation. And so this is one view of it. So let's take another view. So this is another angle looking at the same star cluster. And since I'm a space aviator, I want to fly around stuff, right? So let's just do a fly around. Oh, it works this time. So this video or this visualization, I want you to see what the key point is. the distribution of gas is really clumpy. So this clumpy gas distribution will significantly change how radiation or starlight interact with the gas and how starlight and gravity interacts. And so I will end with this visualization. So once more, superstar clusters are very dense and bright, and they're amazing. And please check out astrobyte.com. Thank you very much.
All right, thank you, Space Aviator. So we'll take a few questions.
The question was, how long is the time scale? So for the superstar cluster formation that you just saw, is 300,000 years. So it's less than 1,000,000 years. So it sounds like a lot of time, but in astronomical time scale, it's really short.
Okay, up front.
Okay, based on that question that they form very quick, and that's the way a lot of the blue supergiants form, is that mostly what forms? There's large blue supergiants? What type of stars typically do you get?
So the question is what type of stars that I get in my simulation. So if you go into the details of because this is a very large scale simulation, we are simulating the whole gas star forming giant molecular cloud, and we cannot resolve individual star formation. So, but most of the star will be massive star. So stars above 10 times solar masses. Yeah.
Over here. Up here. Up here.
Okay,
Yes.
up there. Way to be vocal.
So the question was, what am I most surprised about in my research? So, you know,
You can answer both questions.
I think I'm surprised every day, because just comprehend this whole exercise, right? So we didn't know anything about this, but by looking at the stars, like the galaxy that we just saw and the star cluster that we just saw, and originally we didn't know anything, but by just thinking about physics and trying to build very sophisticated computational models and actually do the simulations, you just get a piece of how the universe works, and that is the most surprising to me. Yes.
Oh. Go ahead. Sir?
So the question was, is Milky Way containing any superstar clusters? So that is a very tricky question, because what defines a superstar cluster actually depends on who you ask. So if you ask me, everything under 1,000,000 solar masses is not a superstar cluster. But on that, for specifically for that question, people think there are two, like most like the biggest star cluster in Milky Way. But yeah, the sizes vary. It goes from maybe a couple thousand solar masses to close to 100,000 solar masses. Yep.
Go ahead.
So the question was, what differentiates a superstar cluster from a globular cluster? So the typical belief is superstar clusters are the precursor, or they are they comes before globular cluster. If you look at the simulation, if you keep the simulation running, let's say for 1 billion years, you will, at the end of the day, we believe that will produce a globular cluster.
Okay, I saw that gentleman first.
How long did it take your simulation to run on the supercomputer?
Okay, the question was, how long did my simulation run on the supercomputer? It took about 2 weeks on 1,000 CPU, so it's a long time. So because of the supercomputers, we typically use hundreds to thousands of CPU at the same time. We just connect them together, put in the physics, and then let all the CPUs to do the calculation at the same time for an extended period of time. If you do it on your cell phone or your laptop, it may take, 20 years.
That's a nice cell phone. Okay, one more question. Do you still have a question?
There's
Okay.
one there.
All right, right there.
So, just curious, you gave the example of the Sun and Proxima Centauri.
Yes.
These stars are much closer together than the Sun and Proxima Centauri would be, or about the same distance?
They are much closer. So the Sun and the Proxima Centauri is feel 4 light years across, right? So these star clusters fit in within that 4 light years.
So would you say that these individual stars are less likely to have planets orbiting them because they're so much closer to each other?
Yes, I would think so. Yeah, because we look at that. We have you can't see the stars right there, but imagine there are million stars right there. So the starlight is really intense. So whatever gas around it, that will be destroyed by the radiation.
They're going to be incorporated into the star instead of being made up into planets.
That's the last follow-up.
Yeah. So the process that goes inside the core of that superstar cluster is kind of complicated. We still don't know for sure. We don't know a lot because resolving that very core of superstar cluster is very hard. And currently, we don't have any computational simulation that can resolve that spatial scale.
All right, let's thank Benny one more time.
Thank you.